This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Today we have reached Lecture 9 in our course. Our topic today will be the very important and useful idea of iteration, or repetitive execution. In C, this is done with loops and sometimes with nested loops. We'll look at the while statement and the for statements today. Two comments before we proceed into the material. One is that today I will be focusing on the basic concepts and the syntax needed for iteration. In a later lecture, we'll look at some principles of loop development and give you some guidelines for finding loops and implementing them in your algorithms. I'd also like to mention that the structure of today's lecture consists of quite a large number of fairly small examples. Let's start with what is now an old friend, our program to convert Fahrenheit to Celsius. You remember this program. It does a printf to ask for a temperature, scanf to read in a value, computes the answer, and then prints it out. There's nothing wrong with this program. In a traditional sense, it completely meets its specification. But if we think about it as a real user of the program, we might wish that it worked a little differently. For example, the user can only type in one temperature and have it converted when the program runs. Might be kind of nice if we could convert several temperatures. This would involve repeating code that's already in the program. Another thing you might notice if you run the program is that if you type in bad data, the program will do something unexpected with it. It might terminate abnormally, or it might just give the wrong answer. That's not very nice either. It might be nice if the program detected this and then repeated the steps for asking the user for a value and reading it in. Both of these enhancements involve the notion of repeating something, repeating steps that are already in the program. This sort of control flow is new. We haven't seen it before in our programs, but it's something that algorithms frequently need. We call this a loop, a section of repeated code or repeated steps. Like conditionals, loops will add a tremendous amount of power to our programs. There are many algorithms which simply cannot be performed, or that is turned into C code, using the kinds of control flow we know up to this point. Now, when we learned about conditionals, there was quite a bit to learn, quite a bit of syntax and some concepts. The same will be true with loops. However, I might just alert you in advance that loops conceptually are a little trickier, and even experienced programmers may have trouble getting them right. So just be patient. Eventually, you'll get the hang of it. Let me show you another example where loops may be helpful. The problem here is to add 4 numbers entered at the keyboard, the sort of thing you might need if you took 3 friends to lunch and offered to pay for all of them. You could do this on a calculator. How would you do it in a C program? I think you could all sit down and code this now, and your solution might look like the code you see on the screen. We first have to read in the 4 numbers. This could be done with a single scanf, and then we could have a single assignment statement to print to compute the answer. Although I haven't shown it, the program would have to continue by displaying the answer or doing something with it. Such as saying, gee, if I'd known you guys were going to eat this much, we would have gone somewhere else. Now, the code we have so far is fine. It does meet the specifications. However, if you took 13 friends to dinner, think about how you'd have to change the program. Think of how messy it would be with 13 variables to declare, a huge scanf, a large sum. And if you took 39 guests, it would be even worse. And what if you had 4,000 guests in Key Arena? It would get pretty unwieldy. There has to be a better way to do it. And the way to do it is to find a way to express the algorithm using repeated steps, which our first version of this problem didn't do. There is some repetition buried in it, though. Let's rework this algorithm so that we can make this repetition explicit, and then I'll show you how we can turn that repetition into a loop in C. Here's another way to get the same result of adding up the 4 checks. The difference is, instead of reading in all the numbers at once and then adding them all at once, I'll do one number at a time. A perfectly reasonable and normal way to proceed. Go around the table and at each person add one more number to a total. Now, to make this work, I'll have to start the total at 0. Then I'll have 4 sets of repeated statements. Each one is a scanf followed by an assignment statement. This is perfectly good C. Now I'm going to show you how we can rewrite this using the syntax of the C while statement. Don't be panicked if everything on the slide doesn't make sense. It will in just a few slides more. Here is the same algorithm expressed without having to write these pairs of statements 4 times. You see the yellow box. I've got that same pair of statements, but written only once. However, when the program executes, that pair of statements will be performed 4 times. What makes this happen is this magic new keyword while, which says repeat the statements following it. Now, you won't want to repeat those forever, so one of the tricks to writing loops is figuring out what conditions are those that make you want to do the repetition. That condition is shown immediately following the while loop in parentheses. If that looks a little bit like the syntax for the if statement, you're absolutely right. The syntax of these 2 statements, if and while, is very similar, but their meaning is different. Before we leave this example, let me point out one way we could generalize it. If you have only 4 people, the program I just showed you works fine. How could we make it work when we don't know in advance how many people are going to show up for your lunch party? In that case, we would want to put something in the program that asks, as the program is running, how many checks there are to add up. This is easily done with a printf and a scanf. As you see there, the first pair of printfs and scanfs. Then, the trick to making the loop execute the right number of times is shown in the second box, count less than number of inputs. If you remember on the previous slide, we said count less than or equal to 4. Simply by changing that to count less than or equal to number of inputs, I'll be able to make this work however many guests I'm paying for the checks. Here's the syntax of while. It looks a lot like if. In fact, the only difference is a new keyword while instead of if. There's a loop condition that, like the if statement, has to be in parentheses. And then there's a loop body. If there's more than one statement to be performed multiple times, as there very often is, then you form them into a compound statement, as I've shown here, using curly braces. Our friends curly braces help us out here once again. Let's move to another small example. Here, the problem is to compute 7 factorial. Remember that mathematical symbol means the product of all the integers starting from 1 up to and including that number. So the definition of 7 factorial is very easy to write down in a C assignment statement. Just by its definition, x gets 1 times 2 and so forth up to 7 gives us the right answer. If we want to write a more general set of statements to do this, that could compute 9 factorial or 27 factorial or something, a loop sounds like the right thing to do. But as I made the first draft of this program, there isn't any explicit repetition. I need to rewrite, try to tease out the repeated or possibly repeated parts of this algorithm before I can apply loop formation to it. Now we see three steps along this journey to a loop. In the far left column, we see the multiplications broken down into bite-sized pieces. This is already very promising. The difficulty is that all of these pieces are slightly different. The first one is x gets 1, the next is x gets x minus 2, and so forth. They're not quite the same. I need some kind of a trick that will make all the repeated code look exactly the same. Well, one way to do this would be to look at the parts that is different and see what I could do with it. Seems that the different part has an integer value that's first 2, then 3, then 4, and so forth. So the trick I could use is to replace that integer constant with a variable and then change the value of the variable every time. The nice part about this is the value changes in the same way every time. I add 1 to it. So in the middle column, I see that kind of new regularity. All the lines are the same except for the first one. All of them say x gets x times I, followed by xi gets I plus 1. Now that we have something that's identically repeated, I can form it into a while loop, or at least the part of it that is the same. The first line, x gets 1, I gets 2, can't be put inside the loop because it is different. So we'll leave it outside the loop, and we'll take x gets x times I and I gets I plus 1 and put it inside the loop body, as you see there. Let's examine this loop body, or this whole program in fact, to understand its control flow and use the notation we've seen before for flow charting. There's a decision to be made: is I less than or equal to 7? Every time we come to this point, we'll ask that question, and the answer could be true or it could be false. If the answer is true, we'll continue and do the loop body, you see in the yellow box on the right. And following that, the arrow goes from that box back to the decision point. This is where the while loop differs from the if statement. Think about where this arrow would go if we had if instead of while. Instead of going back to the top of the decision, that arrow would continue to the same place where the no arrow went. Now what about those two statements that were different? They have to be done, but they're not part of the loop body. So we show them at the top being performed exactly once and then flowing into the decision point. Let's trace this loop. I have to say in advance that tracing sometimes is a process that can put you right to sleep. If you promise not to sleep, I'll promise I won't go to sleep in front of you. So let's start stepping through it. As usual with a trace, we want to keep track of the values of the variables. We want to step through the statements in the same order that the CPU will do when the program executes, and keep track of the changes and the flow of control as this process goes on. I'll keep the variables in a little table on the right-hand side of the screen. I've labeled each line of the program with a letter A through G, and I'll preserve that line in the table to show us where we are at any given point. The two variables I and X each have their own column. After line A executes, I has still an unknown value. We haven't initialized it yet, but X has a 1. After line B executes, we know the values of both of those variables. And now where are we? Well, we've entered the realm of the loop. Every time we enter this realm, we will check the condition. The condition, I less than or equal to 7, might be true or it might be false. To help us keep track of that, let's add a final column on the right that tells us whether that is true or false. Let's mark it T or F. Now, the first time we get to this point, I less than or equal to 7. Well, we look up the value of I in our table, and we see that it's currently 2, and ask, is 2 less than or equal to 7? After deep thought, I've decided that that must be true. So I write a T in the column on the far right. And at this point, following the meaning, the semantics of the while loop, I will enter the loop body and follow its control flow until I reach the end of the loop body, the trailing curly brace. Okay, let's do that. We're now in the loop body, which is two lines, D and E. The first one changes X with the multiplication. You see that happening in the trace there, in line D. And the second one changes I by adding 1 to it. Okay. Now here, coming up, is maybe the most important step of this whole trace. So if you're catnapping a little bit, wake up with me and think about, where do we go from line E in the program? If you're thinking F, you're still half asleep. But if you're thinking C, as I'll bet you are, you're dead right. We get to the end of the loop body, we'll always go back to the top of the loop and check the condition. Okay. So now we're back at line C. The values of the variables have changed a little bit, but the comparison is still true. 3 is less than or equal to 7. That will cause us to continue into statements D and E. From there, we'll go back to C. If the condition is still true, we'll do D and E, and we'll keep doing this. Eventually, I will be 7. Is 7 less than or equal to 7? Yes. So we'll go and we'll do D and E again. You see the values that by this time we have in I and X. We get to the trailing curly brace. We go back to C. And now, is 8 less than or equal to 7? It's not. So I have an F in the far right column. And here is the other really critical point of this trace. When the condition is tested and it is false, as soon as it's false, the while loop ends. You do not re-enter its loop body. You go to the point just past its loop body. Looking at the program, that's line G. And we have now completed tracing this loop. Okay, that may be tedious, but that's exactly what the CPU is going to do when it's given the program to execute. And although you don't want to have to do that very often with your own programs, you have to be able to, you have to know how to do it when occasion arises. Let's take another example. As I said, we'll have lots of small examples here. Let's suppose your dear old aunt has promised you $1,000 if you can pass this course. Well, you tell her thanks. Secretly, you're just a little disappointed it wasn't $2,000. You could buy that new multimedia computer you've had your eye on. But you say thanks. And there is a way to fix that. All you have to do is put the money in an interest-bearing bank account. And in some number of years, you'll have the $2,000 and you can buy that wonderful computer. So here's the problem we want to solve. Figure out how many years it will be until you double your money. Interesting thing about this problem is we don't know ahead of time how many times the interest needs to be added. That is, how many years are going to pass. In the problems up to this point, we kind of had that number in mind, but we don't anymore. It's the answer, in fact. So we want to put together a loop, and the answer to the overall problems will be how many times did I go through that loop? How many times did I add interest? Here's some code for it. We'll start out with a variable for the money. I want to have $2,000. So I should stay in my loop as long as what I have is less than $2,000. This means I'm leaving the money in the account. I'm going to wait a year and add the interest. The interest is easily calculated. My money gets my money times 1.05. Okay. Now, I could stop there for the loop body, except I want to know how many times this is happening. So let's keep a count of how many years. Initially, when I first put the money in, no years had passed. If I use n as a variable for the number of years, that will start out as 0, and each time through the loop, we'll add 1 to it. When my money is finally at least $2,000, I'll leave this loop and print the answer. Now, to make this loop work, we not only had to get the loop body right, but we had to get the variables initialized to the right value. If I had forgotten to set n to 0 before going into this loop, I wouldn't get the right answer. In fact, I don't know what answer I would get because I don't know what value was in there. This points out something important about loops. In order to get them right, you have to carefully initialize any values that are going to be used inside the loop. Okay, ready for another example. Here the problem is taking a bunch of numbers and finding the average of them. Now, two things are a little bit different about this problem compared to, say, adding up all the checks. Here the number is not given, but the means by which the number of values is given is specified. It's hinted at there in the printf statement, which serves as our specification for this problem. It says end with -1. What we are using here is a trick that is often employed in programs like this, where an unknown amount of data is to be entered. The idea here is that we never expect -1 to be a valid value in the problem. So we can use it for a special meaning. We're going to use a -1 to mean that we're done, that there are no more numbers. Okay? This is called a sentinel, a special value that has a meaning other than its normal use as data. Rather than go through this in detail, I'll ask you to spend some time looking at this on your own. Convince yourself that the program works correctly. Take a look at how the while loop is coded and see if this notion of a sentinel is properly implemented. Let's move on to another example. This one will introduce a brand new concept. Problem is to print the diagram you see there. Sounds quite a bit like another problem we worked on intensively a few lectures back. The first time we saw functions. You remember we had the print banner function that printed 2 lines of asterisks. We're doing something very similar here. We're going to print a little simple 3D pattern that contains 3 rows of 5 asterisks. You could all write this program using a series of printfs. In fact, you could write a single printf that would solve this problem. But there is some repetition here, and since we're studying iteration, let's see if we can tease it out. If you stop to think, we're doing something 3 times. We're printing 3 lines. But then as you look closer at each of those lines, you say, that's also an iterative operation, because each line consists of printing 1 asterisk 5 times. So what's the loop? It seems like there are really 2 loops involved. 1 loop to print that prints lines, and 1 loop that prints a line, prints the data within a line. Can we do that in C? Could I have a loop within a loop? You can answer that yourself if you think about compound statements. A principle that we learned was that you can have any kind of statement in a compound statement. So why not have another while loop? That's perfectly all right, and that's exactly what we need to solve this problem. Let's do it in 2 stages. Let's first write the loop which prints the rows. Now, there are going to be 2 loops, and people use the terminology inner and outer to refer to these. The outer loop prints a row every time through. That loop will have to keep track of how many rows it has printed, so we'll declare a variable rows for it and assign it to 1 initially. The loop condition has to be set up so that we go through exactly the right number of times. Here I've followed good programming style, and I've taken the constant 3 and made a pound-defined symbol out of it. If you think about it, you'll see that this condition, rho less than or equal to capital Rhos, with the initialization I've shown, will cause the loop to execute exactly 3 times. Now, I'm not done yet because I need an inner loop that prints that row. This is shown in the white box. Everything else is the same as on the previous picture. The same kind of analysis leads us to write the inner loop. What we do inside that loop is print a single asterisk. We want to keep track of how many times we've been through it, so we have a variable called call to do that. We have to make sure we initialize call to the proper value corresponding to the way that the loop condition is written, call less than or equal to calls. Think about this, and I think you'll agree that it gives the right answer. Nested loops quite often occur in implementing our algorithms in C. Let's trace this program. It'll be most easy for you if you have a hard copy of it in front of you as we go through this. I've changed the format a little bit from some of our previous traces, so I'm going to keep the values of row and columns horizontally instead of vertically. I'll also be showing the output, which is not a variable. It's what appears on the screen as we proceed. There on the right-hand side is that program. It may be hard to read, but you can refer to your hard copy if you have one handy. Well, instead of having lots of question marks all over the place, I'll just use blank spaces on the screen to indicate values that haven't been set yet. The very first statement of the program initializes row, so it now has a value. Then we step into the outer loop, the while statement, and as always, the first thing we do is evaluate the condition. We're going to compare the variable row to the constant Rhos, which is 3. Is that condition true or false? Well, at this point, it's true. So we'll enter the loop body. Notice what the first statement of the loop body is. Its call gets 1. So now we have a known value for that variable. Okay? And the next statement in the program, surprise, is another while. So we've got to apply this process to the while loop we have here and completely finish that while loop before we go on in the outer while loop's body. The condition being tested here is call less than calls is 1 less than number of columns, 5, and it is at this point. So we'll go into the inner loop body and do a printf, and that puts 1 asterisk on the screen. Following that, still in the loop body, we'll add 1 to call, and now it becomes 2. We'll go back, check the condition again, it's still true. We'll re-enter the inner loop body, put out another star, add 1 to call, and we'll keep doing this. Adding 1 to call, printing another star. Eventually call will become 5. The condition is still true. Call gets call plus 1. Call becomes 6. Now, I'm at the point call less than or equal to calls. Is that true? And this time, for the first time, the answer is no. 6 is not less than or equal to 5. Okay, now where do we go? This is pretty critical. Where do we go at this point? The condition call less than or equal to calls was just found to be false. If your answer is we go to printf \n, you are dead right. That's what we're going to do next. Following that, we'll do row gets row plus 1. That will change the value of the variable. And here's another critical point in our trace. Where do we go then? And the answer is we've reached the closing curly brace of the outer loop. Whenever we do that, we reach back in time to the whiles that corresponds to it. Which one is that? That's the one whose condition is row less than or equal to Rhos. Make that test now. Is 2 less than or equal to 3? And the answer is yes, it is. We'll go back in the inner loop, the outer loop, excuse me. Call gets 1. Okay, we're reinitializing call. And then we get to the test call less than or equal to calls. That's true. Okay? This is quite important. We've reinitialized call. It doesn't pick up with the value 6 that it had at one point. We're starting over with 1. Okay. So we're going to march through this code. I think what you should agree happens is that we'll do this 3 times in the outer loop. Eventually, we'll reach a point in the inner loop where call is 6. So it will terminate. It will go to the next statement in the outer loop, the printf \n. Then row gets row plus 1 makes row 4. We're checking the condition now of the outer loop. Is 4 less than or equal to 3? The answer is no. So where do we go? We're finally done with this fragment of code. You're probably glad. And if you've understood this trace and reproduce it, then I will be glad too. Let's look at another example. Lots of examples of loops. They really do occur very frequently in algorithms. Here the problem is to print the multiplication table. Now this is just a little piece of one. When I was in school, we had to learn the tables at least up to 9s. Perhaps education is advanced so far now that students learn them up to 19. Or maybe they don't learn them at all. I'm not quite positive. But everybody remembers what the idea is. You want to find the product of two numbers. You look in the row and the column corresponding to those two numbers to see the answer. So if we want to know what 4 times 2 is, we look in row 4, column 2, and that box has an 8 in it. So that's the value in the multiplication table. Our job is to print this little figure. Now let's not worry about the lines and how they got there. We'll just worry about getting the numbers in the right order in the right place. In a later lecture, by the way, we will talk somewhat about graphics, and you would learn how to print lines and to format things like this. At first glance, there doesn't seem to be much repetition involved. However, if you rewrite the entries in the table as products, then a really startling pattern starts to emerge. As you look across any of the rows, you see that the first number is always the same, and the second number is going up by 1. See that? If you look down any column, you see that the first number is increasing by 1, and the second number is always staying the same. So we're starting to see some suspicious-looking similarity. In fact, it looks quite a bit like the similarities to the factorial problem. We were able to tease that apart and get that turned into a loop. Let's look at the process of just printing one row, say the row for 2. Okay. So as we go through the entries in the row, what we're displaying is first 2 times 1, then 2 times 2, then 2 times 3. It looks like we could do this with a loop that kept that first number, the 2, constant, and changed the second one. So using what we already know about setting up loops, we could write this to make sure we go through exactly 3 times and to make sure that we have the values initialized. Okay. Now, that solves the problem of this particular row. We need to do every row, and that will involve a nested loop, as you probably suspected. Okay. The outer loop controls row printing. Each time through the outer loop, we'll print a single row. Each time through the inner loop, we'll print one box within that row. Notice that in the value we printf inside the inner loop, we're using both of our loop control variables, row and column. In the slides, I have a trace. What I would suggest that you do is try to trace this program on your own using any notation that's convenient, maybe using boxes or maybe making columns of the 2 variables as I've done here. And then see if it matches what I've got as a suggested answer. If it does, then I would say you have a good grip on the material that we've covered so far. Just a few notes now before we step back and plunge back into syntax. Loop conditions really are just conditions. There's nothing special about them because they're in loops. Conditions also occur in if statements, and all of the things we've learned about conditions and complicated conditions and compound conditions and so forth, all of that applies to conditions used in loops as well. One of the most important things to remember when analyzing and tracing a loop is that the condition is reevaluated each time through the loop. So it may be true at first, it may be true many times, but we can't rely on history. We have to reevaluate every time. Eventually, if the loop is going to ever end, that condition will have to be false. One extremely common type of a loop condition is checking to see how many times we've been through the loop, see if we've reached a certain number. Most of the loops that we've seen so far have this pattern, and it's extremely common. One that did not, by the way, was doubling your money. We did not know ahead of time how many times we were going through that loop, but we did know in many of the other examples. This involves keeping a counter, which of course has to be initialized so that you go through the correct number of times. This pattern occurs tremendously often in algorithms, and because of it, programming languages like C often have a special statement type that is ideally suited for this kind of counting, the for loop. C++, Java, many languages have for statements similar to the one I will show you for C. Let's go back to a familiar problem, computing a factorial. Let's say n factorial, where n is already given to us in some form. We saw how to program it using the while loop. What I'll show you now is the same algorithm with the for loop. The code on the right will achieve exactly the same effect as the code on the left. Now, it looks quite different. The syntax is different, and there are some details here we'll have to master, but essentially the same process will take place. Here is the syntax, and it is fairly bizarre, a bit more complicated than any of the statements we've seen so far. Part of it looks like familiar syntax. There's a new keyword for, and then at the end you see a compound statement. That's going to be a loop body. What's different are the three parts that are in the parenthesis. This is no longer a simple condition. There's more to it than that. Of these three parts, the first is initialization. These are things that will be done just once before the condition is ever checked. The second part is a condition, and it corresponds exactly to the kind of condition we saw for the while loop. It's checked at the same points. It has the same kind of meaning. Do the loop if the condition is true. Do the loop body if the condition is true. The third part is quite new. It's sometimes called the update expression. It's hard to know exactly what to call it. But what this is a statement that will be executed after all the statements in the loop body each time. Okay. This is better shown with a picture. Here's a for loop. The initialization is done only once. So from it, we flow to the condition check. Is that true or false? Well, if it's not true, we'll end the loop. We won't do any more checking. We won't execute the loop body. If the answer is yes, we'll do the for loop body. And up to this point, the control flow is quite similar to the while loop. But then, when the for loop body is finished, we'll do the update expression every time. This is a bit weird because the update expression is written near the top of the for statement, but is executed near the bottom of the processing. One way to try to understand this syntax is to compare the for and the while directly. You can always rewrite a for as a while and vice versa, but in doing so, you move things around. Initialization is not a built-in part of the while statement. So if you're using a while, you still have to do initialization, but those will be statements that appear above the keyword while. Whereas a statement of initialization in the for loop is within the syntax. It immediately follows the parenthesis. The condition is in roughly the same place. And what about the update expression? Well, if I have a for loop, I could get the same effect by taking its update expression and writing the while loop that has the update after what would normally have been all the statements of the loop body for the while loop. Notice this means the update has to be inside the curly braces. If it were not, it would never be executed until the condition was false. We want it to be executed every time after the loop body has finished all of its other statements. Counting is something that we do a lot of in computer science. For loops are well adapted for that. There are a lot of ways we could count things. If I asked the man on the street, the woman on the street to count from 1 to 10 or to count up to 10, they'd probably start with 1 and continue to 10. Here, that's what I'm doing in this loop. I'm starting with 1 and I'm counting until n. So I will do this loop each time that n has a value, count has a value of 1, 2, and including 10. On the other hand, if I stopped a random person on the street and asked them to count to 10, they said, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I would know that I had found a C programmer, because that seems to be the way C programmers like to think. You will constantly see this style of counting in C programs. Start from 0 and go up to, but not including, the number you're counting to. This gives you the same number of steps as the previous one, but the actual high and low values are different. 0 through n minus 1. Let's go back and redo a previously solved problem using a nested for loop instead of a while loop. This was the problem that printed 3 rows of 5. We've already analyzed this problem in great detail, so we know what the condition should be. We simply have to move the code around a little bit to get it in the form required for correct execution by the for loop. In fact, by a nested for loop. The problem, the algorithm, still involves nested loops, so instead of nested while loops here, we'll have nested for loops. See if you can convince yourself that that works. Let's move on to a similar figure just for practice. This looks more like a right triangle. We're getting into a little bit of our graphic analysis in some of these problems. Think about that for a minute. It differs from the previous problem in that we're not putting the same number of stars on each line. It differs. In fact, one way to look at it is that on row 1 we put 1 star, row 2 has 2 stars, and so forth. So abstractly, we're printing row stars on each row that has that number. Okay. It's another nested loop. Because we're counting things, and we know ahead of time how many things they're going to be, the for loop is the natural way to express this. The outer loop counts from 1 to rows as before. The inner loop counts from 1. But here is where it differs from the solution to the previous problem. In the inner loop, instead of counting up to a fixed number of columns, we're counting up to a variable. If you locate this with me in the second part of the second for, call less than or equal to row. Both of those are variables. This allows us to do a different thing, a different number of executions every time we execute this loop. Here's another challenge. At first you might think, well, I'll just reverse something or other in this picture and I will be all right. It's actually slightly more subtle than that, because the stars don't line up on the left, they line up on the right. The way to analyze this is that on each line you're starting by printing some spaces and then you're following that by some stars. How many spaces do you print? Well, that number depends on which row you're on. And if you analyze it carefully, you'll find that the number of spaces is 5 minus the row number that you're on. That's the kind of analysis you have to do before you can write the program. And that's really the hard part. At first, the syntax of for and while might seem daunting, but eventually you realize that You've mastered those. The hard part is doing the analysis in order to set up the algorithm right, not to express it in C. The answer to this one, surprisingly, involves 3 loops, or perhaps it's not surprising now that we've thought about it. The outer loop, one for each row, and then 2 inner loops, one that does spaces and one that does stars. Something else to look about tonight while you're reviewing the material. Now, it is true, although it may not seem like it now, that the syntax isn't the hard part of programming. It's only hard at first until you're familiar with it. There are a few famous pitfalls that I need to point out to you, just as there were for the if statement and conditionals. Here's one of them. This is a perfectly innocent looking little piece of code. It seems as if we have a while loop that we're going to go through some number of times, depending on what sum was first initialized to. The pitfall here is a punctuation mistake. Following the condition, there's a semicolon. That's bad news. Now, maybe what the programmer wanted, but it probably is not. That semicolon terminates the loop body. It's just as if you had empty curly braces right in front of it. So instead of sum get sum plus 2 being inside the loop body, it's outside this loop altogether. And what will happen? Well, you'll just keep checking sum less than 10. And sum is not going to change because there's nothing in the loop body to change it. The loop body is empty. So you either won't execute this more than once or you'll be in it forever. Being in a loop forever is a common problem. A common bug in programs is called an infinite loop. The same kind of pitfall occurs with the for statement. The semicolon at the end of the first line terminates the loop. Here's another type of bug, slightly more subtle. We want to terminate this loop when I is not 10. Now we start I at 1, and we're going up continuously by 2, so you might think eventually I is going to reach 10 and we'll stop. Now think about it. What are the values that I takes on? It's going to be 1, 3, 5, 7, 9, 11. Yeah, 13, 15. It's never 10. So this loop never ends. Bad news. Here's another kind of danger, one you might guess at from what we said before. Remember, the doubles aren't necessarily exact replicas of real numbers. They might have small round-off errors. So I've got a double involved in my loop condition, x less than 10. Okay. Now, this is correct syntax, and it's going to run, and it's going to do something. The problem is that due to round-off error, x may not have exactly the values we had in mind when we set this loop up. What we probably expected was that we get answers like those on the left-hand side. And the last time through the loop, the value would be 9.8. Then x would go to 10, and the condition would be false and we'd fall out. If instead, due to round-off errors, x was slightly less than that, we would not only have x, the condition being true for x at almost 9.8, but we'd go through the loop one more time. Probably not what we want. So here's my advice. Don't use doubles as loop counters. Try to set up the problem so you're using integers and then perhaps do some conversion or some calculation in order to get the answer you want. Take a look at this later and see if this doesn't also make sense. We often count in loops. Most often we count by 1. We don't have to. We could add any other number, positive or negative. But it's very, very frequent to count up by 1, or as in the second example here, count down by 1. This happens so often that there's some special jargon for it. Increment means to increase a value, most often by 1. Decrement means to decrease. In the dictionary I received as a high school graduation present, these words occur, but they're not verbs. That's new jargon that's been introduced to the language by programmers. In C, there are a couple of operators that make it convenient shorthand to do these frequent operations. They're called post-decrement post-increment plus plus, and post-decrement minus minus. These have the effect of adding 1 or subtracting 1. And when used by themselves, they work exactly like x gets x plus 1 or x gets x minus 1. They're very, very often seen with loop counters. Let's summarize what we've seen today. General pattern for iteration is to initialize, do a test, do some stuff, the loop body, and then go back and repeat starting with the test. For and while are equally general, but for is preferred for stylistic reasons by most programmers when counting is involved. In a later lecture, we'll talk about designing loops. We'll talk about complex conditional expressions, which are extremely handy with loops as well as for if statements. And then we'll be ready for arrays, a very powerful new way of organizing data, which is often used in connection with loops. I look forward to those lectures. Please join me then.